Hi, welcome to section 16.2. The iPad is still down, and so I'm doing this through video recording. And so we're just going to talk about line integrals. Really not a hard section. You just need to know how to plug in and know how to do parametric equations. And so in this section, we're going to define an integral that is similar to a single integral, except that instead of integrating over an interval a to b, we're going to integrate over a curve c, such that integrals are called line integrals. So what we're going to do today that's going to make things just a little bit different from, I guess, Calc 1 is, instead of, finding an integral that's of a straight line, now we're going to find an integral that's going to be of a curve. And so here you see on the right the kind of curve that we're dealing with. All right, and what we're going to do is we're going to look for and try to find the area underneath that curve. And so we're going to be able to do that with line integrals. Now, we're used to doing this with straight lines in Calc 1, Calc 2, but now what we're going to do is, because this isn't a straight line, in order to be able to find the area underneath that, more than likely what we're going to have to do is we reparameterize our function in terms of a single variable, usually t. So I have x equals x of t and y equals y of t, where we're just going to reparameterize both x and y into functions of t. And then we're going to evaluate our integral from a to b using our new variable t, which usually we're going to do as time. Now, we're going to divide our curve into n sub-arcs with lengths delta s sub 1, delta s sub 2, and so those are going to be the basically our little Riemann sums underneath our curve. So it's very similar to what we did in Calc 1, where we found Riemann sums underneath our line, and that helped us find the area underneath the curve. So in this formula, what we're going to do is we're going to take our height. So because this is going to be a function that's still going to be in 3 dimensions, we're going to be able to find the height of our line integral, our curve, by f of xy, and then the length of each subarc is going to be defined by delta s. All right, and so it's going to give us this equation, the integral, and again, we're going to denote this by c of f of xy ds, where f of xy is going to be the height and ds is going to be the arc length. Again, recall that because ds is equal to arc length, we actually know how to formulate that. And so we're going to have our new formula of how to evaluate line integrals, and this is the formula that we're going to use today. The integral from a to b of f of x of t, y sub t, so we reparameterize x and y. So again, this is the height times the length, and because we're taking an integral, we're taking a bunch of Riemann sums of it. And so since ds is arc length, it's the square root of the partial of x with respect to t squared plus the partial of y with respect to t squared dt, and then we're going to be able to evaluate. And so what this is telling us is that, okay, the area underneath our curve is going to be defined by this equation, all right, for line integrals. And this is what we're going to base everything off of today.